same at all places. Therefore, when we have a change in one, we have to have changes in others to compensate so that the total is still the same. So the four problems we have set up: calculating H for a particular part of a system, H being total energy from one side of this system, which you guys have this problem 3.36. How do we deal with a split is number two. Adding some vena contracta to our estimates is number three. And then number four is what's a profile of energy change as if we were to put holes in the side of a container to watch it drain out. All right. So real quick, I just wanted to mention for homework 7, in part 2, you might get a negative H. I altered the original problem, and when I did that, I didn't realize I was going to get a negative H value. So just FYI, that's not a bad thing. Just go ahead and tell us what it is. It would be accurate. It would be accurately solved if you got a negative H, I believe. So, and then in part 3, consider embracing vena contracta there, which is where you've got fluids on two different sides of a wall. We've looked at that before with respect to pressure forces adding up on that wall, whether they're in balance or not. But in this case, now we've got an orifice in that wall, and so the two different levels mean that we have flow from one to the other. So go ahead and invoke our coefficients, the contraction coefficients for that particular problem. All right. Alexi, did I miss anything?
I think that was all for the written homework. Yeah.
Okay. Terrific. Emma, anything from you?
Good.
Good. Okay. Terrific. All right. Let's go ahead and get started then. 50 minutes goes by quickly when you're having fun. Okay. So again, I'm not going to rewrite the Bernoulli equation because we'll rewrite it a few times. But this is the same slide we had at the beginning of recitation last week. Just to note, remember, we're talking about pressure energy, kinetic energy, potential energy, and remember that we can show those or express those to the Bernoulli equation essentially in terms of head or in terms of pressure. So all of these could have basically set up as pressure, a kinetic pressure, and a potential pressure, or we can show this as a pressure head, kinetic head, potential head as well, or elevation head. All right. Okay, so let's go ahead and get started here with the first problem then. Streams of water in particular, so if we're going to use a gamma, we're going to use that for water, from two tanks impinge upon each other as shown below. If viscous effects are negligible and point A is a stagnation point, determine the height H. So a couple of things. You'll note that we have a tank over here on the right-hand side, and that tank has a height of water in it of 8 feet. And then above that, we have this air gap, and we have a pressure of 25 psi above that 8 feet of water. And so that 25 psi is pushing out some amount of water that comes up from a jet from the bottom here. And then we have another jet coming down from above where water is freely flowing out of this upper tank. Okay. And so what I'm going to do here is just identify the top of this location as point number 1 and the top of this surface as point number 2. And the reason that I'm doing this is that those are two places where I can evaluate a couple of things that I will need to know, right, for the Bernoulli equation. One is a height of the surface, right? So I can do that with 2, although it includes H, and we don't know H yet, but still we can represent it. Whereas if I go a foot below 2, or I'm somewhere in that upper reservoir, I don't know exactly where I am. On the other hand, at point number 1, we know that that's 8 feet from what we'll go ahead and call a datum here, Z equals 0 for this sort of floor position underneath all of this. And then we're noted that point A is a stagnation point. Okay, so of course that means that VA, right, is equal to 0, and we know that ZA we are given is equal to 20 feet. Okay. And we could go through this with 1 as well. What we're going to, just ahead of time, I want to note that we're finding a number of we're simplifying the Bernoulli equation. We'll write it out in a second. From a couple of different directions here. We note that all the total H at 1 has to equal the total H, big H, so this is now all the energy at point 1 has to equal all the energy at 2, has to equal all the energy at A. So we can break this up into 2 pieces. So H1 is equal to HA, and we can also say that H2 is equal to the H at A, and therefore H1 is equal to H2 as well, all right? So we need to think about how we put this together and how we use this information. So I'm going to start with working on the first piece of this, which is to indicate, let's see, let me get a couple of other things written out. So we said P2, of course, is going to be equal to 0 here, and Z2 is equal to 20 plus H, or 20 feet plus H. V2 simply, or simplifying our lives a little bit, is 0, right? There's no velocity occurring at the surfaces of these reservoirs the way we've been dealing with them in the past. We note that VA is 0, ZA is equal to 20 feet. We note that P1 is equal to 25 psi. I'm just writing this underneath because I ran out of space over to the right there. V1 is equal to 0, and Z1 is equal to 8 feet. Okay, so we could start either direction. I'm going to go ahead and start with this representation here, that H2, the total energy at 2, is equal to the total energy at A. All right, so if we write this out, I'm going to write the long form and then we'll cancel things. P2 over gamma plus V2 squared over 2G plus Z2 is equal to PA over gamma plus VA squared over 2G plus ZA, and now we can cross out a bunch of these. So we said P2 is equal to 0, we said V2 is equal to 0, and we said that PA is also equal to 0, and VA is also equal to 0, right? So basically, we have these two. Wait a minute, did I goof something up here? I should not have. I did not. Oops, I goofed that up. Sorry. This should not have been equal to 0. We actually have a pressure in there, and it's because of these two streams meeting. Sorry, this was about to be Z2 equals ZA, and I went a little too far. So our pressure head still is included here simply because, so let me, maybe just to be clear, I'm just going to scratch this out and add it to the end, PA over gamma. And the reason for this is that we have, I realize that we have these two streams that are meeting and then deflecting off of each other, but essentially there's still a pressure head of water coming down vertically from above. Okay, so we can't ignore the fact that there is vertical movement of water here, which is providing something of a pressure. Okay, that's why this looks a little bit different than some of the other cases that we've looked at with our free jets. The free jets that go out into the world and sort of, go out horizontally for the most part, those tend to have that pressure equal to 0. In this case, we have a slightly different situation, okay? We do know what ZA is. Okay, so...
I have a quick question about H1 being equal to HA and H2 equal to HA. Like, where did you get that?
That's just my shorthand for not writing out the entire Bernoulli equation for both. Right, so all this is saying is that all the energy at 2, remember capital H we were using last week is equal to basically all of this. This is all H2, and this, and this is all HA.
Okay.
Right? That's all it is. It's just a little shorthand to keep all of us from writing out too much. Okay. So the next step then, let's simplify this. Basically, Z2 we said was 20 feet plus little h. And remember, little h is what we're looking for, is equal to, we have PA over gamma plus, and then we said that ZA is equal to 20 feet. Okay, so this simplifies to basically these 20 feet cancel on either side. H is equal to PA over gamma. Okay. All right, so that's our column of water here above A, but we still don't know what H is, right? So this makes sense from the perspective of saying that the pressure that is pushing down, the column of water that's pushing down on A is H high, right? And so PA over gamma equals H is probably something we could have predicted without having to necessarily prove it this way. All right, I'm going to go to the next slide now so that we can work from 1 to A to help us figure out what H is going to be, okay? All right, so now we have P1 over gamma plus V1 squared over 2G plus Z1 is equal to PA over gamma plus VA squared over 2G plus ZA. And now we said before that we have P1 is equal to 25 PSI, V1 is equal to 0, and Z1 is equal to 8 feet. So, and on the, we also have, we're going to retain PA over gamma and ZA. So the only thing that will cancel on the A side is this guy right here, right? That kinetic term. Okay, so V1 goes to 0. So now we have 25 PSI over, I'm just going to write over gamma for the moment just to simplify. We'll do the substitutions in a second here. Plus 8 feet is equal to PA over gamma plus ZA here, which is 8, sorry, not 8, wrong side. This is 20 feet. Okay, so one thing to note here then is recall that we could replace this from our previous equation on the previous slide to just be H, and then we can solve directly for H, okay? So we can rewrite this now. Let me think. I think what I'm going to do is move that. Yeah, I'm going to isolate the H on one side. So H is equal to, we're going to have 8 feet minus 20 feet, right? So that'll come out to a negative 12. But then we're going to add, we're still going to have 25 PSI, and then we're going to multiply by 144 inches squared per feet squared to just convert that pressure into pounds per square foot. And then we divide by 62.4 pounds per foot cubed, okay? So when we go through, even with this minus 12 that we're going to get from the differences in the feet, sort of the elevations, we're going to end up with H being equal to 45.7 feet without accounting yet for sig figs. And it looks like we've got a bunch of single sig fig values in there, or at least one, 8 feet. So, you know, that's probably going to end up being 50. But in any event, if you do this math, you should come up with 45.7. And then when you account for sig figs, you would get the 50. Okay, does that make sense to everyone? I think part of the simplification that we got from going from, recall this was 2 and this was 1. Going from 2 to A just gave us that H was equal to PA over gamma, which we could then plug in to the second relationship for the Bernoulli equation from A from 1 to A in that case.
Could we have instead done this from 1 to 2?
You could have done it from 1 to 2. Let me think about that for a second. You would have had, so this would have been the left-hand side. I think as long as, yeah, your H would still be in there. Yeah, you probably could have, actually. Let's see, did you have enough information? So on this one, you knew P, you knew Z. On the 2 side, all we had was Z, which was in the form of A. So, sorry, in that's 20 plus H. So yeah, you probably could have. Yeah, good call.
Thanks.
Yep.
What's a good rule of thumb then for deciding like which 2 points to start out with?
So for the most part, you want to choose often these surfaces like this, right? That those are places where you're either going to be given a pressure or you're going to assume that that pressure is equal to 0 because it's open to the atmosphere. Hopefully you also have some heights, some reference heights to get to that location so that you've got an elevation that's included. In this case, the other point in the middle here, obviously, you were given that that was a stagnation point, so that was part of the target in this case, right? Without knowing that that was a stagnation point, you might have been a little unsure and you might have gone from 1 to 2 to figure this out, which should also be valid. Does that make sense?
Yeah, thank you.
You bet. Okay, is it okay if I go on to the next problem? Okay, terrific. All right, now I'll read through this, but then I just want to take a moment to make sure that we're all on exactly the same page here. So the Y fitting shown here lies in a horizontal plane, so we're basically looking down on it. The fitting splits the inlet flow into 2 equal parts. So when you say splits the inlet flow into 2 equal parts, that means that you can see here Q2 is equal to half of Q1 and Q3 is also equal to half of Q1. Okay, so just as an FYI, that's an important component of this. At section 1, the water velocity is given here, so V1 is equal to 12 feet per second, and the pressure is 20 psi gauge, so P1 is equal to 20 psi. Okay, calculate the water pressure at sections 2 and 3. Assume in viscid flow and a water temperature of 60 degrees C. So P2 is equal to what, and P3 is equal to what? Oh, 0. Sorry, is equal to what? Okay, so those are our targets, and we have the diameter at Q1. We're also given the velocity straight up, so we're not given the flow though. So one of the things that we should be able to do with the diameter and the velocity is calculate the total flow, right? That's going on at 1. Now we may want this because we're told that the flow, the total amount of volumetric inflow on the left at 1 is split in half to go into legs 2 and 3 of this pipe. And so that means then we are given a diameter for each of those, the legs 2 and 3, but we're not given anything about the velocity. So one way that we can figure out the velocity at 2 is to say Q1 is equal to Q2, and of course this means V1 A1 is equal to V2 A2, and the thing that we're given here, we have this, we can calculate this, and we can calculate A2 to basically back out V2. Okay, and we could do the same thing with 3. Oh, I'm sorry. Q2 is equal to. Let me add this. Let's finish this thought. So this would be plus V3 A3, but because we know that Q2 is equal to 1/2 V1 Q1. Pardon me. We should be able to figure out that velocity at both 2 and 3. Okay. And I guess we should say Q3 is also equal to Q2. Okay. The other thing then that's really important here is when, again, we're going to think about, our velocity head, our pressure head, and our elevation head. And we note that this is all in a horizontal plane. So we're looking down on it. What that means is, of course, that all of our z's are identical. So we are assuming then that regardless of the fact that the diameter at 1 is 6 inches, the diameter at 2 is 3 inches, and the diameter at 3 is 4 inches, that all of the centers of those are in the same plane. And so z does not play a role here in the context of our total energy equation. All right? Okay. Oh, a different stagnation point. Sorry, that got left over from the previous slide. Sorry about that. Okay, so let's see what we can do with this. Well, the plan that we have is we're going to use continuity as we outlined here to figure out those velocities at 3 and 2. And then we're also going to apply the Bernoulli equation along this path and along this path. So we can do it from 1 to 2 as well as 1 to 3 to figure out these pressures. Pressure at 2 and pressure at 3. Okay. All right. So let's start with 1 to 2. Okay, so we're going to start with P1 over gamma plus V1 squared over 2G is equal to P2 over gamma plus V2 squared over 2G. And the thing we don't know is P2, right? We are given, we're given P1, we're given a velocity at 1. This is the thing we're looking for. There's our target, and we can calculate V2. All right, so let's do that real quick then. So we said that Q2 is equal to basically pi over 4 times D1 squared, and then we're going to multiply that by 1/2 essentially. Okay, so in other words, that's just 1/2 Q1. All right. And so that comes out to a value of, let's see, so this is, I guess, let me take it one more step, pi over 8 times d squared, which is 6 inches at 1, so that's 0.5 feet. We're going to square that, and that comes out to be 2.36 feet cubed per second. Okay, so that's sorry, what did I do here? Nope, that was Q1. I was just calculating y. I took that a step too far. So this would be 1.23 is what we should get. Sorry, 1.18. I gave you Q1 instead. Sorry about that. So 1.18 cubic feet per second will be Q2. And now we need to figure out V1 or V2 rather, pardon me. So V2 is equal to I guess Q2 over A2. And so this is equal to 1.18 feet cubed per second divided by, and then we have pi over 4 times D2, which is 3 inches. So I'm just going to do my math real quick. 0.25 feet. That's diameter squared. And I actually don't have this calculated, so let me calculate it real quick. So we have 1.18 times 4 divided by 3.14 divided by 0.25 divided by 0.25. So I get 24.0 more or less, 0.04, but I'm going to call it 24.0 feet per second for V2, all right? So now we can come back to this and solve for P2, all right? So we can say P2, actually, I'm going to make this a little simpler by multiplying everything by G, and that'll just get rid of the G's and just leave us with rows. I guess that doesn't matter too much. Well, does it? Nah, well, we'll leave it in terms of gamma. All right, so P2 is equal to gamma times P1 over gamma times, let's see, so I need to add V1 squared over 2G times gamma, and then we subtract V2 squared over 2G also times gamma, right? So those are our three terms. And so what we end up with is P2 is equal to P1 plus V1 squared over times rho divided by 2 minus V2 squared rho over 2. Okay, so I just was simplifying there a little bit. So P2 then comes out to be P1, which was given as 20 PSI. So we can convert that now to 144 inches squared per foot squared. So that'll convert that into pounds per square foot for us. And then we add, we said V1 was 12, is that right? Yeah, 12 feet per second. And then we're going to square that quantity, and then we divide by 2. Oh, I forgot to multiply also by my density of water here. Oh, rats. I did this. Okay. So this is a little bit different. Let's see. I need 62.4 divided by 32.2. So 1.94 slugs per foot cubed. And then we're going to subtract this 24.0 feet per second quantity squared over 2 and multiply by, again, 1.94 slugs per foot cubed. Okay, so this is P2. So P2, when you work this out, should come out to be 17.1 PSI gauge, which is then the same units as the 20 PSI gauge that we were given at point number 1. Okay.
Could you go over why, when you're solving for Q2, you didn't do V times A? You left out the velocity term.
No, that's what I did wrong. Sorry. Okay, this should be Q2, so it's Q1 divided by 2, so this should have been 12 feet per second. Thank you for that. The number is correct. I just didn't include it there. So this also needs to come in right here. I had the solution correct. I just didn't write out the full equation. Sorry. Thanks for that, Emma. Anything else pop up? Okay. All right, so that's P2. Let me see. I think I didn't give myself, I did give myself another slide. All right, so let's go ahead and work this out for P3 as well. If we go through the same process, essentially note that, so Q3 is equal to, what was that same value? It was 1.18 feet cubed per second, and that's equal to A3 V3. So to solve for V3, we have 1.18 feet cubed per second divided by pi over 4 And then D squared here, this D is 4 inches, so this is 0.33 feet quantity squared. Okay, so V3 comes out to be, let's see, 1.18 divided by 0.33 divided by 0.33 and then times 4. Okay, I get 13.8 feet per second. Okay, so a bit higher velocity, which makes sense, right? Just a quick gut check. We calculated. Hey, wait a minute. Nope, that's the wrong direction, isn't it? We calculated V2 is 24. Where did I go wrong here? Maybe I should check my 24 here. Am I going to be missing? Let's see. 1.18 divided by 3.1415 times 4 divided by 0.25 divided by 0.25. Now I still get 24 there. Oh, no, that's right. That's right. Sorry, I swapped the diameters in my head. No, that's right. So this diameter is larger than this one. And so it makes sense that our velocity comes out lower, right? We have the same flow going into both 2 and 3. So just as a quick gut check, it makes sense that V3 should be a smaller, should be a smaller velocity because it has the larger diameter, so the larger area. All right. So now if we go back, we can write this equation for P3 is equal to P1 minus, well, let's see. I don't want to skip too many steps here. Let me start over. Let me start from the beginning. So P3, P1 over gamma plus V. That's just not nice. Plus V1 squared over 2G is equal to P3 over gamma plus V3 squared over 2G. And we're looking for P3. So once again, P3, just like we did for P2, is equal, that's supposed to be an equal sign, is equal to gamma times P1, let's see what I want to do here. Move that to the other side. So this is going to be P1 over gamma plus V1 squared over 2G minus V3 squared over 2G, right? G is 32.2 feet per second squared. Our gamma here is 62.4. So P3, I can just write this out the long way instead of all the simplifications. 62.4 pounds per foot cubed is, we're going to multiply that by P1, which was 20 PSI times 144 inches squared per foot squared divided by 62.4 pounds per foot cubed. Then we add V1 squared, we were given as 12 feet per second. We're going to square that term divided by 2 times 32.2 feet per second squared. And then we subtract V3, 13.8 feet per second quantity squared divided by 2 times 32.2 feet per second squared, and put a bracket on the end of that. And all of this will yield P3 being equal to 19.7 PSI gauge. Okay, so I, again, putting it back into the native units that we were given for P1 and not doing pounds per square foot. Okay, any questions on that? Thanks for catching my error on the flow rate calculation on the previous slide.
think you're good.
Okay, terrific. Okay, so now in this problem, determine the flow rate through the submerged orifice below if the contraction coefficient is 0.63. Okay, so we expect that the higher energy, of course, is on the right-hand side, right? We have 6 feet of water stacked up. We expect water here to be stacked up, and it's going to be moving from right to left because on the left-hand side, we only have 4 feet stacked up. Okay, so we have higher energy. We always go from high energy to low energy. So essentially, we can go from 1 right here, as you might expect. So again, with respect to whoever asked that question earlier about why would we start here, we know that V1 is equal to 0. We're given a height here. So Z1 is equal to 6 feet, and P1 is equal to 0, okay? But if we want to know the flow rate through a 3-inch diameter hole, okay, and we're not really told that it's round, but we're told orifice, and more importantly, we're told diameter, then we expect that it's round. And so we need to set up a couple of points down here of interest. So I'm going to set up point number 2 out here and point number 3 right in the middle. Okay. So we can apply, let's see. So if 2 is right in line with 3, and those are halfway up the left-hand water column, then we know that Z2 is equal to 2 feet. Okay, and we also know that P2 over gamma is equal to 2 feet. Okay, in other words, that's the pressure of the fluid stacked up above us, right? Now, we don't yet know what V2 is, okay? So V2 is a mystery at the moment. So that's something we'll have to solve. At 3, we would kind of have the same problem, except in this case, you can see we're given this contraction coefficient. We're going to end up using that to figure out 3. Okay, so what we're going to do is essentially apply the Bernoulli equation from 1 to 2. And then 3 gets solved only because we need the velocity there. We don't actually have to deal with any of the energies there. But rather than include the contraction coefficient in the Bernoulli equation, we're going to do that after the fact. So we're going to do this in 2 steps. All right. So the first thing is to figure out the velocity at 2. 2 is right outside of 3, or just beyond the orifice. Therefore, once we figure out that velocity, we can back up and figure out what the velocity is inside of 3, and therefore the flow rate in there. All right. So P1 over gamma, of course, plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2, right? Now, let's see. Oh, I guess we have all the things we need for 1 as well. Okay, so this comes down to, so what did we say? The P1 goes to 0 and V1 goes to 0 as well. So we have Z1 is equal to, we added that, we don't know that, we have 2. Okay, is equal to P2 over gamma, basically is 2 feet. I'll just write it in. We'll substitute all the numbers here in a second. P2 over gamma plus V2 squared over 2G plus, and then we added Z2. We know what Z2 is. So this comes out to be Z1 is 6 feet The only thing we don't know is V2 is equal to 2 feet plus V2 squared over 2G plus Z is, we said that was 2 feet as well. Okay, so now we can solve for V2. And I'm just going to skip that step here, but all you're going to do is the algebra, right? To figure out V2, don't forget to take the square root here. But that will come out to be 11.34 feet per second. All right, so there's step one of this part. So if that is V2, then what we need to do is note, I'm going to do this on the following slide, but now we'll use the Q is equal to V times A to figure out exactly what the flow rate is. Okay, so move forward here, Q through that orifice is equal to A2 V2. A2 is a little bit nebulous, but what we really mean here is that it's C, or contraction coefficient, times A3 times V2. Okay, V2. So V2 and V3 are basically the same. I could have written this as V3 and said that they're identical, but essentially we can't have, there's a point beyond 2, of course, that the velocity dissipates. We're using 2 right now to just get us beyond the orifice, which is where 3 is. All right. So this would be equal to 0.63 for our contraction coefficient times, we had 3 inches divided by 12, which would give us feet. Then we're going to square that. We multiply by 11.34 feet per second. And when you work this out, you end up with a flow rate of 0.351 feet cubed per second before you account for significant figures. Okay, so A3, all we were really doing was penalizing that cross-sectional area to make sure that the right velocity and area were accounted for there. Alexi, was there something that popped up?
Yeah, someone just asked in the chat why P2 over gamma equals 2. I think that was on the last slide.
Yeah. So P2 over gamma has to equal this pressure of overlying water in this case, or whatever fluid it is. And because we know there's 2 feet above us, then that head is represented as 2. So, but that is different than the 2 that is the elevation head above the bottom. Okay. So if this was 5 feet deep and 2 feet off the bottom, we would have a 3-foot pressure head above us and 2 foot of elevation head below us. Okay. Okay. So, how are we doing on time? Okay, we're almost to the end. All right, go ahead and so what we're going to do with this is I'm going to collect your responses to this. So we have 3 options here, A, B, and C. And then what we're going to do is work through this last problem to prove to ourselves which of these is the correct answer. So for now, without the benefit of working through it, I guess you could guess, but several holes are punched into a tin can as shown in the figure below. You'll note that the top of the tin can, by the way, is open to the atmosphere. Which of the figures represents the variation of the water velocity as it leaves the hole, and why? Okay, so let's go ahead and get that started. We'll give you guys a minute to respond here. So go ahead and try to reason through it, and then we'll go through the sort of mathematical proof for which one should be the correct answer. A, B, or C? after we get all of the votes in, I'll just note on this so we can come back to this slide what the results were, because I think I'm going to lose it when I close the, when I move on to the next slide, when I close the iClicker or Reef app that we have open here. All right, 85, is that pretty close to how many we have? How many do we have? We have 88, 87. Okay, that's pretty good. That seems great. All right, so let's go ahead and stop and take a look at the data. All right, so it looks like, so we had 38 here, 26 here, and 23 for A, 23 votes. Okay, so now let's go through the mathematical part of this and figure out which one of these is real. So I'm going to do that on the next slide, and I'm going to close this app to be able to do that, right? Oh, sorry. Oh, that's fine. This is the only one I had set up anyway. All right, so, hello. Curious. Oh. Okay, so let's see which is real. All right. For any of these locations, we could start at a point right here, call that 1. And again, from the perspective of the Bernoulli equation, this is advantageous because P1 will be equal to 0. Z1 will hopefully have a defined value, right? We'll know something about that elevation. And V1 is going to be equal to 0. So we're converting all of this potential energy into some kind of kinetic energy coming out at some location. So let's just, we're going to have some flow line that we expect to basically do this. Maybe it's a little too hard of a curve there, but essentially point 2 will be down here, okay? So what we want to do is write the Bernoulli equation between these 2 points, and then what we need to do is think about how these things are going to change as we move down, right? Because we're going to have another option that does that and that all the way down, right, with these 5 different holes, okay? So let me go ahead and write these things here because I gave myself a blank slide, but I forgot to repeat the picture on the next slide. So V1 is going to be equal to 0, and we said 0, and P1 will also be equal to 0 because it's open to the atmosphere. And then Z1 is going to be equal to like whatever the height of the water is, right? And with a tin can, this is important because we expect this is not an infinite reservoir. So as we're losing volume, of course, that H is going to drop through time. So I'm just replacing Z1 with H in this case. P2, then at this open jet, P2 will be equal to 0, and we'll have some Z2 equal to some H2, right? So H, we could call it H1, I guess, but H1 and H2 will not change. I mean, we'll have to consider how we move down through the height, but essentially we should be able to sort of figure out some kind of relationship here, right? So with that in mind, let me switch. Oh, we don't know what V2 is yet, but we're gonna keep our. This is gonna help us sort of solve the Bernoulli equation and think about how things change with depth. Okay, so let's write out the equation. P1 over gamma. We'll start with our basics plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2. All right, so we said that V1 was equal to 0. We said P1 was equal to 0. Z1 is basically, I'm just going to call it H1 to distinguish from H2. P2 we said was also equal to 0 because we have a free jet. We don't know what V2 is, so H1 is equal to V2 squared over 2G, and then plus some H2 value. And the reason that I wrote this in terms of H1 and H2 is to just get away from those very distinct Z values that we would start with. So we can basically rewrite this and say that V2 is going to be equal to the square root, as we've talked about before, of 2 times G times H1 minus H2 as it works out. And so another way to write this is that the difference between h1 and h2 could be a variable value h if we wanted to. But the point being here that if we were to draw a curve of 0 to h for v2, it would look like this based on the fact that it's a square root, okay? Based on the fact that we can solve the Bernoulli equation for this square root sort of a function. And therefore, we could think about 0 h falling through time, and what we would end up with then, because v2 has this sort of a response, we would expect this sort of a velocity distribution, okay? So going back to that original figure then, I'll let you guys write this, and we're just about done here. Just got another 30 seconds. I'll just let you guys finish this for a couple seconds. Then I'll go back to the original slide, and we'll take a look at these distributions. Okay, so if we go back to this, that means that, let me go back to the other one where we voted. That means A would end up being the winner, okay? So, we didn't take time to really think through the Bernoulli equation reasoning for this when I asked you guys to vote, so no problem. Part of this is sort of a gut check on what should this look like. One thing I will point out is I can see where any of you would have chosen any A, B, or C. The only thing I would say about B that's a little bit funny is that it's often very strange to see such straight line responses in nature or physics. So that, that is important. We do have a straight line that's sloping when it comes to thinking about hydrostatic pressure distribution because of the changes with of piling up water, and that's a consistent pressure increase with depth. But in this case, with velocities included, it's more likely we would probably have A or C. In this case, it just worked out to be A, okay? All right, any questions on that before we break for the evening? Alexi, did anything come up?
I think the problem before this, I think you forgot to write a pi over 4 somewhere, but I guess.
Okay, I'll go back to that. And, I'll just real quick, does anybody have any questions on this before I go back to that one? Okay, terrific. Let me go back here then. Oh, yep, I forgot it right here, didn't I? So here's d squared, and I forgot pi over 4 at this very last one. So thank you for that. Getting ahead of myself. Sorry, my apologies. But that should definitely have a pi over 4 in it because we have the area A3 times V2 times our contraction coefficient. Okay. All right. Well, if there's no other questions, I'll look forward to seeing you guys tomorrow afternoon, and I'll have this posted within, as soon as it's ready from Zoom to be available to you guys via Canvas. So if there's nothing else, I hope you have a great night. Take care.
Thank you.
You bet. Thank you.
Thank you.
Take care.
Quick question for you just about the clicker points. Is it based off of what you get right and wrong?
No, we only care. So in some cases I may have like 6 of them or whatever. I'm just looking for binary. Were you there? Did you answer? That's
okay.
Yeah.
Do
So
you mind just taking a look at mine? Because I think it was just inputted incorrectly because I sent you an email too.
Oh yeah, let me see. Did I? No, I have Abigail Small asking about attendance, not yours. Do you know which dates?
No, I just saw the grade come through on Friday, so.
Okay, let me know which dates in particular. I just want to make sure so that I can check them. There's something kind of weird going on in that I'm not getting the entire class synced over to Canvas, which is kind of a pain. So I need to figure out, we still have the information over in Reef, but trying to translate that over might just mean us typing a lot of 1s and 0s. So, but let me know which one if it looks like it's an error.
Yeah, the only one was, I guess, from today. It said I didn't check in after I checked in, so I don't
Oh,
know.
that's weird. Okay.
Yeah.
So let me. Today is the 9th.
The 8th.
8th.
Yeah.
3, 8. Okay. Okay. Let me see how that translates, but I'll make a note of it. I've got a little list